Starting a new topic today, that is second law of thermodynamics. Now, this one is slightly, you can say, more theoretical, and you would require more attention. Unlike the first law, which we are very familiar, and in case of first law, there are not much variations. It's easy to grasp. But this second law of thermodynamics is slightly complicated, and you need to understand it properly, that what it means actually. Okay. So we have talked about the origin of this second law of thermodynamics, how it has come about. Actually, if we recall, we talked about two types of perpetual motion machine. The first one was that it is impossible to construct a machine which will operate in a cycle and produce net amount of work without net amount of heat being given to it. So that was the first kind of perpetual motion machine. That means you cannot run a machine continuously without giving any energy into it, and on the other side you are drawing energy from it or work from it. Okay. Similarly, there is one more type of perpetual motion machine. Why you call it is a perpetual motion machine? Because if your machine is not perpetual, you want to go out of the class? So if your machine is not perpetual, you can do it. You can violate so-called law of energy. That means without giving energy, you can draw the energy, work, and that you do from the storage within the system. Right? Similarly, when you talk about the second type of perpetual motion machine, again, if it is not perpetual, you can do it. So what does it say? That it is impossible to construct a machine which will exchange heat with a single reservoir and do net amount of positive work. So what does it mean is, it's not asking you to violate the first law. It's not saying that you are not inputting any energy. Okay, you continue to put in some energy into it. You put heat into it. Still, if there is only one reservoir, then you cannot produce any work out of it in a continuous way. You are not violating the first law. You have a reservoir, you have a source at a high temperature where heat is available. You take out heat from that reservoir, convert it into work. It is not possible if you have a perpetual motion machine. Now, when people observed this, that they found that we require a minimum 2 reservoirs to do this work, to get the work or to make an engine, then that experience was converted into a law. So, as I also told you, that law is not a theorem. There is a difference between the two. Law is, you can say, you have put all your experience into a concise statement. That becomes a law. And the only justification for the law is that it has not been broken so far. Otherwise, there is no sanctity for it. Why it should be so, nobody knows. But it is like that. A similar example is that time always flows forward. You cannot go back in time. Now, that is an experience. Nobody can say, yes, you cannot go back in time. You cannot prove it. But our experience is that we cannot go back in time. We know that everybody will die. That is an experience because we have no person who is living maybe more than 200 years, 100 years, 150 years. A day comes when everybody dies. But that doesn't mean that everybody has to die. There is no such, you can say, there is no such uh, governing principle that everybody must die. No, there is nothing like it. It's only an experience. It's only as what we have observed that we have put into a concise statement. Similarly, this second law of thermodynamics, as well as your first law of thermodynamics, both these laws, their sanctity is your experience. You have been observing it for years and years, so many people, thousands of scientists for hundreds of years, they have observed it and they found that they are not being able to bypass this law. Whatever the process is, whatever the system is, wherever they go and do it, they have not been able to break the law of conservation of energy. And when they came to it, that mass gets converted to energy, they modified it that mass and energy are same basically. So mass and energy together are conserved. Now, similarly, you cannot make a machine which is running in a cycle and exchanging heat with a single reservoir and doing continuous work. Now, that statement is given by Planck. But behind that, there is the experience of so many people who tried it. Okay. So it says that it is impossible to construct a closed system which will operate in a cycle. So your system has to be closed. It shall be working in a cycle. Draw heat from a single reservoir and do an equivalent amount of work on the surroundings. So if I put it diagrammatically, you see the diagram on your right side. You have a one reservoir which is having temperature TH. You are drawing heat from this Q1. There is an engine which is working in a cycle, continuously drawing heat from this reservoir and doing an equivalent amount of work. W is equal to Q1. We are not saying W is greater than Q1 or W is less than Q1. We are not violating the first law. W is equal to Q1. So such an engine is infeasible. It is not possible. What is possible is, or what happens is, you have one reservoir here, one reservoir here. You draw heat from a hot reservoir and simultaneously you reject some heat into a cold reservoir, right? And then you do a work which is equal to Q1 minus Q2. again your first law is not invalidated. W is equal to Q1 minus Q2. There is no violation of first law. But it says that Q2 has to be greater than 0. If your W is greater than 0, you can have a typical case where W is equal to 0. Then Q2 will be 0, Q1 will be 0. You can say that your engine is working with a single reservoir. You can remove the cold reservoir. No, your W has to be positive. That's an ideal case. Okay, you can say no work is being done, so you can do with a single reservoir. That is meaningless. If your W is positive, that means you are getting some work out of it. You necessarily have to reject some heat to a cold reservoir. This is the second law. Okay. Now, so your W is equal to Q1 minus Q2. You are not breaking the first law. First law is still valid. And if W is greater than 0, Q2 has to be greater than 0. W has to be less than Q1. Right? And what are the important points here? First is we are talking about an engine which is a closed system. That is the first necessity. Now, when an engine is operating in a cycle, what is happening? That there is no change occurring within the engine. So, engine is moving in a cycle, it comes back to its original state. So, the changes are occurring only where? In the reservoirs and the surrounding. From one reservoir, you are drawing the heat. In the another reservoir, you are discharging the heat, and you are getting out some work which is again going into the surroundings. Nothing is happening to the engine. Engine is only facilitating this conversion. Okay. Then it says, we have already talked about this, if W is greater than 0, then Q2 has to be greater than 0 and W is less than Q1. Which also means that heat cannot be converted to work completely. In other words, if Q2 is greater than 0, it means that W is less than Q1, which means that whatever heat you have withdrawn from the hot reservoir cannot be converted to work completely. Which also means that heat and work are different. Because you know that work can be converted to heat completely. Friction is the method. Your vehicle is going, some sliding, some block is sliding on an incline, right? From a height, you have an incline here. The block is coming here. What is happening? The potential energy is getting converted into kinetic energy and then into, by friction, into heat. This is a 100% conversion. All the potential energy goes into kinetic energy and all the kinetic energy goes into heat. Potential energy is a form of work. Kinetic energy of the block, not of the molecules. Similarly, potential energy of the block, not of the molecules, not macroscopic, not microscopic, macroscopic energy. So macroscopic potential energy, macroscopic kinetic energy, they are same as work and they can be converted to heat completely. So one-way conversion is possible, complete 100% conversion is possible. The reverse conversion is not possible 100%. Q cannot be converted to work completely. This is what the second law is saying. You have to necessarily reject part of the heat to a cold reservoir, which means that these two are not same. Heat and work are not same. Okay. Now, then we have already talked about it with a great emphasis that minimum 2 reservoirs are required. Okay. Now, then note that if you are not operating in a cycle, then heat can be converted to work completely. Okay, that is possible. So those things are left out. The system should be moving in cycle. Okay. Now, a similar, you can say, or I would rather say another definition of second law was given by classes. They are both contemporary, working independently. They are studying their experience and the experience of previous scientists. Both came out with a statement which defines second law. Their statements are different. They work opposite to each other, but they are themselves complete in themselves and support each other. We'll see that how these two statements are equivalent. But meanwhile, what it says that it is impossible to construct a closed system which will operate in a cycle. Transfer heat from a body at low temperature to a body at higher temperature without work being done on the system by the surroundings. It simply means if you want to transfer heat from low temperature to high temperature, which is what your refrigerator does or air conditioner does, what these two systems do. So if you have this system, a refrigerator or an air conditioner, what they are essentially doing, they are transferring, air conditioner is transferring the room heat which is at a cold temperature, and the excess heat which is being generated here is being transferred out and thrown into the atmosphere which is at a higher temperature. Same thing is being done by the refrigerator. Only the difference between the two is refrigerator is being used for vegetables and food, other food items, and air conditioner is used for human beings. In refrigerator, the volume is very small relatively, and in air conditioner, it is the whole room which is being cooled. That's the only difference. Their temperatures are different, but essentially both of them are same. Now what it is saying is, clause is saying that you cannot operate your refrigerator or air conditioner without electricity, without doing work on it. It is not possible. You cannot transfer heat from a low temperature to a high temperature without work being done on it. But remember, heat from high temperature to low temperature can be done without your any interference. It happens naturally. All the time heat is flowing from high temperature to low temperature. No external work is required for that. What does that mean? That heat at a higher temperature is not same as the heat at a lower temperature. And remember here again, we are not violating the first law of thermodynamics, and we are not violating energy conservation. We are not saying that excess heat is being transferred. No. Whatever you remove from one reservoir, you are transferring to the second reservoir. From high potential or high temperature to low temperature, it is automatic. You don't have to do anything. But if you have to transfer heat from a low temperature to high temperature, it is not possible without any external work. Okay. And same thing you can see here on the right is a system which is an infeasible system. You are removing heat from a cold reservoir, passing it to the hot reservoir, and there is no work here. Work is zero. So if this is the case, it is not feasible. What is feasible is you can transfer heat from a low temperature to a high temperature when you do work on it. And this Q1 is nothing but Q2 plus W. So what you are removing from low temperature, you add work to it and transfer it to a higher temperature. So work is necessary. Work here cannot be zero. Okay. You can again think of an hypothetical case that TH is equal to TC. Then it is possible. Then Q2 will be equal to Q1 because essentially there is no temperature difference. We want a finite temperature difference between the two. Okay. Now, so what you are getting here? W is again equal to Q1 minus Q2. That is the first law is still valid. Now, as per the second law, if Q2 is greater than 0, you can have a hypothetical case Q1 equal to 0, Q2 equal to 0 and W equal to 0. Suppose you have two reservoirs, one at hot temperature, one at cold temperature. You can have Q2 equal to 0, Q1 equal to 0 as well as W equal to 0. All are 0. That is possible. But we are not talking about that. We are saying that if Q2 is greater than 0, then W has to be greater than 0 and Q1 will be greater than Q2. Okay. Again, the system is a closed system. It has to be closed system. It should be operating in a cycle. That means within the system there is no change. The only change occurring is on the surrounding. You have a hot reservoir which is being heated up again, or heat is being added to it. You have a cold reservoir that is also surrounding. You are removing heat from it and you are getting work from the surroundings on the system. Okay. Or you can say that if W equal to 0, then Q1 and Q2 will be 0. Q1 भी 0 है, Q2 भी 0 है. नहीं चलेगा. ठीक है. So, and if Q2 equal to 0, W will be greater than 0. Sorry, if Q2 is greater than 0, W will be greater than 0. We have already talked about it. Now we come to another concept, that is what is a reversible and irreversible process. Many a times you should understand the exact meaning of the word from dictionary. You don't need to remember the definition. These words are not arbitrary. They have a meaning already built into them. Okay. So always give importance to the meaning of the word. So what is a reversible and irreversible process? Now you have a system here and you have surrounding, and the system is closed, but it is exchanging heat with the surroundings and work with the surrounding. If they are not equal to 0, matlab normally They may be zero, but they are not zero. That means our system is actually working. Now, when do you say that this system is reversible? Now, a system is said to have gone a reversible process if both system and surrounding can be restored to their initial state. Both should come back to the your original state. Normally what happens is, suppose I go down the stair, I come back and sit here again back. It's a reversible process. I have come back to the same place. No, it's not reversible. It is cyclic. When the system comes back to its original state, it is cyclic. But when the system and surrounding both come back to its original state, then it is reversible. So when I go down and when I come back, the surrounding doesn't remain same. I spend work, do the chemical work or muscular work while going down and coming up, which is transferred as heat to the surrounding. In fact, no process in this world is reversible. Whatever you do, even if you move your hand like this, you move your finger, simple finger, it is an irreversible process. You have changed the surroundings. You have affected the surrounding which cannot be restored. So you are not isolated. Whatever you do, you are affecting your surroundings. As a human being also, and as a machine also, as an engine also. Whatever your action is and whatever any system is doing, it is affecting the surrounding. Okay. So reversible is one where system and surrounding both come back to its original state. And in reality, it never happens. But we still talk about it because that becomes a reference point. A reversible process is a reference point to judge all other processes that how much irreversible they are. Okay, that is why we study them. But in reality, we can only think of processes which are reversible. In our mind, in our mathematics, process can be reversible. But in your real life, when you are going to implement it, no process is reversible. Okay, that should be very clear. And by definition, a process is reversible if the system as well as the surrounding both return back to their original state. So if you have a system, it comes back to its state, and simultaneously your surrounding which comes back, it started from 1, followed this path, came back to 1. Okay, it started from 1 point, came back to 1 point, both. Okay, then what is irreversible process? Simple. Which is not reversible, it is irreversible. So there can be only two types of processes, reversible or irreversible. There is nothing in between. Right? Okay. Then there are some important observations to be made, and we will understand them later on, but we can just review them here also. Whenever any irreversibility occurs in any part of the system, the process becomes irreversible. If anywhere there is a irreversibility, then whole of that process, if it includes that irreversible process, then the whole process become irreversible. Uh, it means that suppose you have one system, there is one process going on here and one process going on here. This is a reversible process, this is irreversible process. Now, if you want to talk about both the processes together as one process, then the two together are irreversible. In other words, which means that irreversibility once occurred cannot be offset by any process or any change in any other part of the system. That means if you have a system and in any part of the system irreversibility is taking place, it cannot be compensated or annulled or cancelled by any other thing anywhere in the system. Irreversibility once happens, it happens forever. It cannot be undone. Okay. Which, in other words, which means that even if a part of a system is irreversible, the whole of the system is irreversible. You cannot have a system in which one part is irreversible, the other part is happening such that you combine the two and the both becomes reversible. No. Even the smallest irreversibility anywhere, if it is part of the system, the whole system is irreversible. Okay. In entropy words, we will talk about what is entropy. In entropy, an increase in entropy of the universe due to irreversibility in any part of the system cannot be offset by changes in any other part of the system, because any process at the most, the entropy of the universe will remain same. This is also important, that should I take it after I define what is entropy? So we'll come back to it. Now we talk about this reversibility and irreversibility in terms of entropy. Okay. So far we were talking about reversibility. What definition we gave? That if the system and the surrounding both are restored to their original state, then the system process can be called reversible. Otherwise, it is irreversible. Now let us talk in terms of entropy. But before you talk in terms of entropy, you should know what is entropy. And the biggest confusion mechanical engineers have is that entropy is a measure of disorderness. This is no definition. राम का घर कहाँ है? श्याम के घर के सामने. और श्याम का घर कहाँ है? राम के घर के सामने. और दोनों का घर कहाँ है? आमने सामने. तो आप अपना फिर सर खुजाने लगेंगे कि हुआ क्या ये, अब मैं जाऊं कैसे? You cannot move a step ahead. Entropy is a measure of disorderness. What is disorderness? Is there a measure of disorderness? No. Then what is the point in defining entropy as a measure of disorderness? नहीं, ऐसा नहीं है. इसकी बहुत अच्छी डेफिनेशन है. सिंपल एंड ब्यूटीफुल डेफिनेशन. कहां पर है? स्टैटिस्टिकल थर्मोडायनेमिक्स में. फिजिक्स वाले बताते हैं कि भाई ये एंट्रोपी है क्या. तो एंट्रोपी क्या है कि देयर इज ए मैक्रो सिस्टम. अगर आपके पास कोई बड़ा सिस्टम है, ठीक है, तो आपने उसकी थर्मोडायनेमिक प्रॉपर्टीज नाप ली. प्रेशर, वॉल्यूम, टेम्परेचर, इंटरनल एनर्जी नाप लो, एंट्रोपी नाप लो. एंट्रोपी की तो हम बाद में बात करेंगे. और नाम लो, बाकी भी नाप लो प्रॉपर्टीज, एंड यू फाइंड द प्रॉपर्टीज आर सेम. सो व्हेन यू लुक एट द थिंग, इट इज सेम. प्रेशर भी सेम नापा, जब भी प्रेशर नापा तो ठीक है, टेम्परेचर नापा तो भी सेम है, तो सिस्टम इज स्टेशनरी. नहीं, there's lot many things are going inside. If you talk about this class, इस क्लास में I think 150 benches होंगे, seats होंगी, and about 100 students are here. आज तो कुछ कम आए. But if I look from outside, I may say that there are 100 students in the class. That's all, because that is the only parameter I have. But these 100 students can sit in a thousands and thousands of ways in this room. ये जो पैटर्न है बैठने का, वो बदलता रहता है. आज कोई कहाँ बैठा है, कल कोई कहाँ बैठा है. दे कैन सिट एनीवेयर. ये जो वेरिएशन है, द नंबर ऑफ माइक्रो स्टेट्स, उसका जो मेजर है वो है एंट्रोपी. S is equal to K. K is a Boltzmann constant, logarithmic natural of M. M is the microstates. So for a given macro state, if a system has whatever many microstates it have, that is the measure of entropy. So if you say a system has more entropy, it only means that it has more number of microstates. Right? Macro state is that is measured in terms of thermodynamics. It is one which is measured by P, V, and T. If your P, V, and T are constant, that doesn't mean the air is stationary or it's constant or it is at the same state. For you, the air is at same state. When you meet a person today or tomorrow, he's same. But is he same? Yesterday he was thinking something else, today he is thinking something else. Because you are only looking at the outer. Inside, what is happening? You don't know. You cannot measure it. So many things are happening. नेचर में बहुत ज्यादा वैरायटी है, बहुत ज्यादा वैरायटी है. एंड ईच एंड एवरी मॉलिक्यूल इज एक्सचेंजिंग विद एवरी अदर मॉलिक्यूल. कुछ ना कुछ हो रहा. तो ये जो माइक्रो स्टेट्स हैं वो इतनी ज्यादा हैं, उनका जब हम नंबर कहते तो m का लॉगरिथमिक, k इज ए कांस्टेंट, तो लॉगरिथमिक ऑफ m इज द एंट्रोपी, यू कैन से. So if you have more number of microstates, then your entropy is higher. If you have less number of microstates, your entropy is less. Take an example. I have a box here which has 3 slots and I have 2 balls. How many way I can put it? 3 ways. You can have one here, one here. You can have one here. This is open, or you can have this. Okay. वो है वो नहीं. That is, we are not considering that. Now, if I add one more space to it, how many ways you can fill it? 6 ways. So first you have 3 ways. Now you have 6 ways. What have you done? You have only increased the volume. Entropy has increased. Earlier the microstates were 3, now they are 6. So what happens? The moment you release a gas into a bigger atmosphere, its entropy increases. It can have more number of states. The moment you go out of this class, entropy increases. Because now you have so many places to go, so many slots you can fill in. यहाँ पर आपके पास सिर्फ 150 slots हैं, which you can fill in. Leave this room, go out of the room, the whole campus is there, you can fill any slot. So entropy is more. You are here sitting in an ordered way, you call it an ordered way. Outside you go, you call it is a disordered way. No, it is not disordered. You have a purpose there. Each one has gone with a purpose somewhere. This is not disorder. You cannot say. आपने देखा होगा हॉस्टल के रूम में एक लोग अपने रूम के बाहर एक पोस्टर लगाते हैं जिसमें सब चीजें फैली हुई हैं इधर उधर और उसमें ये लिखा हुआ है प्लीज डू नॉट अरेंज माय रूम अदरवाइज आई विल नॉट बी एबल टू फाइंड माय थिंग्स. उसके लिए वही ऑर्डर है. उसने सब चीजें फैला रखी है, उसको पता है कौन सी चीज कहां है. दैट इज हिज ऑर्डर. एक जो दूसरा आदमी आता है उस कमरे में, उसको लगता है कि यार ये समझ में ही नहीं आ रहा कौन सी चीज कहाँ है. कहाँ तो वो मिलेगा स्टूडेंट, बेड के नीचे मिलेगा, बेड के ऊपर मिलेगा या लेज पे मिलेगा, कहाँ उसका सामान मिलेगा नहीं पता. लेकिन वो व्यक्ति कंफर्टेबल, वो लेज के ऊपर बैठ के वहां कोने में पढ़ रहा है अपना आराम से, टेबल लैंप लगा के. उसके लिए वही सही है, परफेक्ट ऑर्डर है उसका. ही इज वेरी कंफर्टेबल. दूसरे लोग जो आते हैं वो अनकंफर्टेबल है वहां पे. तो ये जो कॉन्सेप्ट ऑफ ऑर्डरनेस है वो सब्जेक्टिव है, हमारे दिमाग का है. जब आप बाहर जाते हैं तो मैं सब कहाँ घूम रहे हो सब लोग, क्या तुमने शोर मचा रखा है. नो, ईच वन ऑफ यू इज मेकिंग ए सेंस. वो अपने दोस्त से बात कर रहा है, कुछ ना कुछ बात कर रहा है, वो उसके पीछे एक पर्पस है, उसमें ऑर्डर है. मुझे ऑर्डर नहीं दिख रहा. आपको पता है ये जो पेड़ पौधे होते हैं और हमने इतने सारे माली लगा रखे हैं कि सुबह शाम उसकी कटिंग करते रहते हैं और हमें लगता है हाँ बहुत सुंदर कटिंग हो गई, क्या एमएनआईटी चमक रहा है, बहुत सुंदर लग रहा है और इतना बढ़िया बढ़िया इसका इन्होंने कटिंग कर रखा है. ये हमारी प्रॉब्लम है. बट हर प्लांट का हर पत्ता इस तरीके से खिलता है कि वो कितनी ज्यादा सोलर लाइट को पकड़ सके. उसका एक पर्पस है, उसका एक ऑब्जेक्टिव है. वो अपने हिसाब से फैल रहा है. लेकिन हमें नहीं दिखता वो, तो हम उसको सीधा कर देते हैं। तो ये प्रॉब्लम है हमारे साथ, ये जो ऑर्डरनेस है, ये जो ये कॉन्सेप्ट सब्जेक्टिव है, इसको आप उसमें नहीं डाल सकते, मेजर नहीं कर सकते, क्योंकि जो एक के लिए ऑर्डर है दूसरे के लिए डिसऑर्डर है, और इसलिए ये जो है डेफिनेशन नहीं बन सकती। डेफिनेशन क्या है कि हाउ मेनी वेज अ सिस्टम कैन एक्सप्रेस इटसेल्फ, दैट इज द एंट्रोपी। एंड वन मोर इंटरेस्टिंग थिंग, मैं इसके ऊपर और बोल सकता हूं बहुत, बट एक फाइनल स्टेटमेंट से आई विल क्लोज बिकॉज द टाइम इज नियरिंग कंप्लीशन। नेचर जो चाहती है आपसे, वो चाहती है आपको मल्टीप्लिसिटी, अपने को डिफरेंट वेज में एक्सप्रेस करना चाहती है, और इसके लिए वो एंट्रोपी कहती है हमेशा बढ़ेगी, हमेशा डिफरेंट डिफरेंट अरेंजमेंट में चीजें बाहर आएंगी। मोर द एंट्रोपी, in a different ways you can express itself. The nature law is evolution. More the mixing, more the spread, more the evolution. That is the underlying principle. और उसको हम कैसे पकड़ते हैं कि एंट्रोपी इज इंक्रीजिंग ऑलवेज। ठीक है, तो ये उसमें अंडरलाइन चीज है।